everyone. So our speaker today is Professor Dinesh Rajan from Southern Methodist University in Texas, and I won't take long on an introduction, but something I should mention is that he got an NSF Career Award last year, and today he's going to be talking about how to improve performance over wireless networks by certain transmission schemes. So without much ado, I'll hand it over to you.
Thanks, Wes.
You can't comment on how many IIT Madras people have gotten.
Not my fingers. Not my fingers.
Thank you, but I can comment on how many of Benham students have got career awards who are in academia.
Yeah, how many?
100%.
Oh, 100. You measured as a percent.
Yeah, it's, I think, I was his 13 or lucky 13 maybe of his PhD students. I think about of the 13, maybe 8 or 9 are in academic places in the US, and all have got a career award. So he never forgot to remind me of that when I graduated and I joined school. So it's a tough legacy to be. Anyway, thanks for the introduction. It's a pleasure to be here. The title of the talk is very informative, as you can see. It's purposefully kept a little vague, and since everybody here is, I think, familiar with the exact areas that we're working in, I'm not going to have too much of an introduction. I'm going to dive right in. This is a talk sort of in two parts. I'm going to talk of two different techniques which basically are to improve performance in wireless networks. So the first one basically is for a single hop. We're going to consider a single link communication, and just to set the picture for what it is that we are considering a standard time varying channel, fading channel, right? And in addition, we are considering a non-constant rate source. It's a bursty arrival of sources. So our objective is basically to transmit this source over that channel to meet a certain data requirement, delay requirement. So the data that comes in has a delay requirement, and we want to meet that delay constraint. All right. And further, we have a standard average power constraint at the transmitter, and we are only going to focus on single antenna, single input, single output antennas in this. Okay. By the way, feel free to stop me anytime if I'm going too fast or if I've made some assumptions that I forgot to mention or anything. Right. So we all know that when you have a fading channel, right, as you wait for the channel to improve and send more packets, your performance is better. Right. Conceptually, we know that, and there are plenty of people who've done a lot of stuff based on that. And so the idea is, as the delay increases, your performance improves. Correct? And this is further under the assumption that you have some sort of knowledge about channel state information. Right? So if you want to write the highs and lows of the channel appropriately, you need to have channel knowledge at the transmitter. Correct? So as you increase the amount of feedback, your performance improves. So you can increase your throughput, or you can reduce your outage in fading channels. And most practical systems have, as we know, partial channel state information at the transmitter. Correct? So what we are basically going to show is sort of quantify this. Everybody knows this effect, right? So we are just going to quantify this and show that how outage reduces as you increase either of these three things. FB is the number of feedback. So if you have more and more information about the channel, your performance will improve better. Right? Makes sense, intuitive sense. And as the delay increases, it improves because you can wait longer and longer to get a good channel state. Or if the channel is in a deep fade for a long time, you can wait it out. So as the delay increases, your outage performance again improves. Or as the SNR increases, of course, the outage improves. Right? So this is all known results, and I'm just going to quickly go through a couple of plots to put that in perspective. And just to come back to our system, we've added a little more complexity. So right now we have a channel estimator. I'm assuming a perfect channel estimator at the receiver, and you have some sort of channel quantizer, and you send some feedback of that channel to your transmitter. Right? And you do some scheduling, which is essentially rate and power control. All right? And based on your randomly arriving packets, which are stored in a buffer. Right? This is basically the system schematic that we're considering. And as I said, I'm going to quickly show what you already know intuitively, which is how outage reduces as you increase the number of feedback. Right? So this shows how the outage reduces. This feedback goes from 1, 2, 3, 4, and so on. And asymptotically, if you have perfect knowledge, this is the outage. This is for some fixed SNR. I just want you to get a feel for how things change as the feedback improves.
What is feedback? What actually don't know what either axis is.
The number of bits of feedback
Per
time slot, if you will, or per coherence interval.
and what's an outage in your system?
Outage is the probability of outage. It's the probability of outage.
Like you mean you send a packet.
You send a packet and
the rate is 2 for the code rate. Is
basically, exactly. So it's the probability that the mutual information is greater than lesser than the rate that you want to send, the size of the packet that you want to send. So the standard outage.
Okay, it's not averaged over time, though, just for a one-time slot.
No, this is averaged over a Rayleigh trading channel. This is for a Rayleigh trading channel with this system that so we put a power constraint P. So that was, I think, SNR of 10 dB or something like that. For an SNR of 10 dB, and the plot I showed in the next slide was for a delay of exactly one time slot. What is the outage that you can get with 1 bit of feedback, 2 bits of feedback, 3 bits of feedback, and so on? Right? The more the number of feedback, the knowledge of your channel is improved. And right now, I've just assumed scalar quantizer of the channel. So that's why I said CISO. So you just take the channel gains, you quantize the channel gains, and as you send more and more feedback, your performance improves.
There's no delay in the feedback channel?
There's no delay in the feedback channel. So it's sort of like an instantaneous, immediately. For each, in some sense, a little non-causal, because for each time slot, you know exactly what the channel is at the beginning of the time slot. So it's not like you know forever at this time, but for each time slot, you know.
So why do you get an outage then?
Because it's a Rayleigh fading, you may not be able to, you have a finite power constraint, and you may not be able to do perfect inversion. So sometimes you have to take an outage.
And the feedback is not complete, it's partial.
It's partial. Even if it are complete, you may have to sometimes take an outage because the delay is limited. There's a delay requirement too. Right? You remember we said this packet.
Particular choice of how you quantize it.
This is for a particular choice of the optimal scalar quantizer. Actually, we optimize the quantizer to minimize the outage. And in fact, we will quantify things a little more. The outage, actually, there are two paths to it. One is actually outage in the channel, and two is buffer overflow. So you might have buffer overflow. So it sort of puts both of them together. I will provide some of the details as we go on, but basically the idea is as delay increases, okay, outage reduces. Seems reasonable.
So it's just a quantization noise in that. It's no other noise in the feedback channel.
In the feedback, it's just quantization noise, correct. So it's just quantization noise for whatever is the number of feedback bits that you have. So asymptotically, if you go to infinite bits, you get this. That's this perfect knowledge. As the number of bits go to infinity, you reach them. All right? And same thing, as I said, as you, this is for different buffer sizes. The curve I showed earlier was just this. I had a different scale on the slide. So this is again the probability of outage of feedback bits as you increase the buffer size. Meaning now, even though you have just 1 bit of feedback, you can wait for the channel because you're allowed a delay of, or your buffer size is greater than 1. Right? Buffer size 1 essentially means that whatever packet comes in has to immediately be transmitted immediately. You cannot do anything about it. Or delay equal to 1. Think of it another way. You don't have the luxury of waiting for good channel conditions. Right? And the other interesting thing that you notice here is that the value of each feedback increases with buffer size. Meaning, if you have, let's say, a buffer of whatever, size 3, or if you are allowed a delay of 3, buffer and delay we'll use in a very loose and synonymous manner. Right? So if you have longer delays or longer buffers, you can afford to wait longer delays. Okay? So if you have longer and longer buffer sizes, the value of your feedback improves. Again, simply because you can wait for good channel states.
Does the buffer size dictate the delay constraint, or is it a separate thing?
Buffer dictates the delay constraint in this case. If you assume, we haven't gone into whether it's a first in, first out and so on, but let's say it's a first in, first out. So as packets come in, and if your buffer is limited, right, you either have to overthrow all the new packets, or if you're sending out packets from the head of the queue, it's equivalent to your delay. That's why I said we'll sort of use a synonymous manner, the size of the buffer and the delay.
Does the arrival rates in the buffer matter?
The arrival rate does matter, and we will quantify all that as time goes on. The arrival rate does matter. It does matter. I mean, if you have very large arrivals, then even what is a size 1? What does size 1 means? Right now I'm sort of using the units of packet size, but it does matter, absolutely. Right? So again, this is still the same background. So the probability of outage versus SNR. As SNR increases, we know the outage decreases. This is for 3 different buffer sizes that we showed, L to 1, 2, and 3, right? For different values of feedback. So for instance, these 2 curves are for buffer size 1 as the feedback goes from 3 bits to infinite number of bits. Infinite number of bits is basically your perfect CSIT case at the transmitter. So if you have perfect knowledge of the transmitter and whatever packet that comes in each time slot has to be sent in that time slot, there's not much you can do, right? I mean, this is the usual channel inversion you do, but because of the Rayleigh fading, you truncate it somewhere and you get an outage. And that is what this captures, right? And as the buffer size increases, this is L equal to 3 bits and L equal to 2 infinite bits. Now you may be able to wait, get significant savings in your outage. It's like almost an order of magnitude savings in outage, right?
So and it seems like the buffer is measured in packets.
The buffer is measured in number of packets.
It seems like the transmission system might transmit fractions of packets or not.
In this case, we have restricted ourselves to a full packet because
so is your choice a full packet or no packet? Or
exactly, it's 0 or 1 for the packet. Correct. We can't. We can do 2 or 3 or 4. It's in integer sizes. We don't break up the packet. So the offline discussion we had, we can do that in fractions. We can break it up into. We assume a fluid model, so you can break up a packet into 77% and 33% and 23%.
Not here.
Not here. Here it has got to go in integral packet sizes. So you can send 2 or 3 or 4 packets in each time slot, which is a coherence interval, or you cannot send 1.5 or 1.25.
The same size.
All are of the same size. So let's assume some common line underlying packet. All right. So just to basically move into what really I want to get to is we know that with channel state information, performance improves. The more the channel state information, right, the better the performance, and it also depends on what is your buffer or your delay allowed and what is your SNR, right? Now what we're going to talk of today, or rather give the punchline, is that there is an exact analog and equal effect wherein just like the knowledge of channel state at the transmitter gives you some benefit, knowledge of this buffer state at the receiver gives you benefit. And that really is the punchline, is to say that if you have some knowledge of you have a buffer at the transmitter, so random packets are coming in, right? If you have knowledge about this buffer at the receiver, that improves your system performance. And that is basically what we are going to show. And the system schematic changes as follows. Everything besides this was what you had before, right? Now let's assume there's another feed forward link. It's like a control channel, right? That sends some partial knowledge about this buffer. So QT is the number of packets in the buffer in the queue at time t. So you quantize it to some value, right? Or you map it to some value, and you send a q hat t using some NF bits, some number of feed forward bits to your receiver. And what we do at the receiver, you have this channel quantizer, right? So this channel, maybe I should step over this side. So this channel quantizer earlier was just taking the channel gain, quantizing it to gamma t, and sending you gamma t hat. Now the channel quantizer has changed such that it's a mapping of both gamma t and this q hat t. So it takes into account what is your buffer state, then does the quantization and sends the information back. And once you have this quantized information back here, you use this along with q to decide your rate and power control and do your scheduling, right? And the basic motivation here is that if the buffer is nearly full, if you know, for instance, the buffer is going to overflow immediately, then you might be willing to take a chance on the channel. Meaning you're going to have your quantizers such that you allow more and more packets to be sent even if the channel gains are not good, right, qualitatively. Right? On the other hand, if your buffer is nowhere close to full, it's only like 5% full, right? Then what you're going to do is you're saying, this channel is not good enough, I'm going to take a chance and wait for the better channel conditions, right? So that's the basic idea, and you have to balance it out with the statistical knowledge of what is the channel statistics going to be like. Is your waiting going to be worth it, or should you take a chance now? And that's how we're going to quantify in the rest of the talk.
I have a question. I think I'm missing something there. What is the use of the feed forward again? Because ultimately the knowledge of the queue is being used in the scheduler as far as I understand, right?
It is being used in the scheduler, precisely.
So why doesn't the scheduler get that knowledge directly from the buffer, and why is
No, the scheduler gets Qt directly. So this, maybe I will go to
So
the...
why is it important? So I'm asking you the same question as you, Greg. Why does the feedback somehow get better with knowledge of
yes,
that?
or yeah.
What do you mean get better?
Or more useful to the scheduler?
It does get more useful. That's the point. As you increase, without this, let's say you got some performance with 2 bits of feedback. If you add this, with the same 2 bits of feedback, your performance improves.
So the question is, what do
It
the
dep-
bits of feedback represent?
This feedback,
No, yeah.
feedback or
The
feed forward?
channel state feedback.
That's the quantization of the channel. So you measure your channel gain. It's a Rayleigh fading channel. You measure the channel gain. You quantize it to 2 bits or 1 bit or 3
So
bits.
if someone told you, oh, there's a big backlog, right, that's fed in the NF.
Yes.
If there's a big backlog, then the 2 bits now mean something different.
Correct. And I will show that pictorially as we go. And that's probably...
Big mystery.
Okay. So basically, in terms of system, what we end up doing now, I'll sort of summarize what we do at the transmitter and what you do at the receiver, and then I'll show you all the plots of how the feed forward is determined and so on. So at the transmitter, you determine the buffer state and transmit this feed forward information, right? And at the receiver, you determine the channel state information, maybe from this because it's again a transmission on the same channel, or using some other pilots or whatever, and you receive this feed forward information. You determine the feedback using the channel state information and this feed forward information, right? And then you transmit that as your feedback back to the transmitter. At the transmitter, once you get this feedback, you transmit data using the buffer state, the original buffer state, not what you sent here, right? You have the original buffer state and this feedback. You use those to determine your rate and power.
So your feedback the number of bits depends on the queue size information, feed forward information, or
The number of bits is fixed. It's a fixed rate feedback beforehand.
So it
You can do variable rate coding, but right now let's say fixed rate feedback. So you say beforehand, my system, I'm going to design it such that it has 2 feedback links, 2 feedback bits and 1 feed forward bit. And we will show even with 1 bit you can do a lot of, it gives you a lot of gains. So the number of bits of feed forward and feedback is fixed. This is number of bits per coherence interval or per time slot.
So what the feedback depends on your, it's a function of something.
It's a function of what the feed forward was and the actual channel. So once you see,
I'm really confused. Maybe I'm asking the same question. It seems
Yeah.
like you're sending some information back and then it's coming back in a loop. So why can't you just send it directly from the buffer?
hold on, maybe the next slide might, maybe this might clarify stuff. So the feed forward that you're sending is this Qt hat, right? It's the quantized value of the actual Q. This is what the receiver gets, all right? What the receiver does is it takes this Qt hat, right? Combines it with gamma t, which is the correct CSIR, right? And it sends you a gamma t hat, which is the quantized channel estimate, basically, right? What the transmitter does, it uses gamma t hat and Qt, not Qt hat. Transmitter has knowledge of Qt, it doesn't need Qt hat. So the transmitter uses knowledge of Qt along with this gamma t hat to find what the rate and power is.
So I guess the system works as follows, right? The receiver somehow combines the knowledge from the buffer and the knowledge from the channel.
Precisely.
The
Precisely.
question is, why doesn't the transmitter combine them instead?
The transmitter only has
So the transmitter could have a channel state.
if
The feedback bits from the receiver,
Yeah.
right, mean something different depending on what the buffer information is that's fed forward to.
if you have infinite bits of feedback, you could do precisely what you said. So in the special case of feedback being infinity, then the transmitter can do precisely that. But the feedback is not infinity. The feedback is finite. So that finite bits meet different things, as he was saying, depending on what the feed forward is.
The Q hat is that.
The Q hat is.
So all this depends on what the scheduler is, right? I mean, you have to fix
The rate and power control. By scheduling, I mean rate and power control. And I'm going to talk about that rate and power control scheme is. It is for a scheme. So we are giving a scheme. We are not necessarily saying this is the best way to use the scheme or something. saying given this class of rate and power control schemes that you want to do, these are the best way to control all the thresholds and so on. So it's a class of schemes. All right. So again, three things happening at the transmitter. You decide what is your, as I said, we are going to use simple scalar quantizer. It's a scheme. You quantize the knowledge of the buffer and send it to the receiver. Right. The receiver uses that quantized knowledge and the exact channel to send you an estimate. Right. And then you use that estimate with the correct knowledge of the Q to determine what the rate and power is. Okay. And so these are the three things that we have to control, that we have to choose. We have to choose what this E function is, G function is, and F function is. Right? And for simplicity, we are going to use the power, the relation given by Shannon's capacity formula for a given gamma and a given rate. We know what the power is e to the r minus 1 into 1 over gamma, basically. Right? So instead of finding both rate and power, we are going to find the rate, and from that we are going to calculate the power automatically. So what I'm going to talk of is a special class of schemes as to how to calculate the rate, how to calculate this gamma, and how to calculate this QT hat. Right? And the objective is to minimize the total packet loss rate. Right? As I mentioned before, there are two packet losses, or rather two types of packet losses that occur. One can be the buffer overflow. For instance, if you have a buffer of size 5 and you get, it's already 4 packets in and you get more packets, it's going to overflow. Right? And the other is the frame error rate in the channel. Right? So two possible places where it can happen. So the first half, what I'm going to do is I'm going to sort of assume that this, because of the way we calculate the power based on the rate, that this frame, I'm going to use outage to measure this frame error rate as an indicator of this frame error rate in the channel. So your standard definition is the mutual information between the input and the output less than the rate of transmission. Then you have an outage, right? So we're going to do an analytical analysis of that. We're going to use outage as a representation of the frame error rate, right? And then of course buffer overflow probability we calculate by setting up the whole thing as a Markov chain. So at the transmitter the Q process will behave like a Markov process, and then you can calculate what the buffer overflow probability from that is. Okay, so what ends up happening is we end up having the optimization is like you want to minimize this error rate over your choice of F, G, and E, the three functions. And so your rate control, your channel quantizer, and your buffer quantizer of it, such that your average power constraint is met. Right? So now let me talk of the special class of functions that we are going to consider. Right? As I said, we are considering simple scalar quantizers for both the feed forward and the feedback information. Right? So what you do, an example, this is just an example of the Q function. So let's say your Q has 1 through as a size of 5. Okay, so you say if the Q is less than 4, meaning 1, 2, or 3, your Q hat is 1. I mean, this 1 and 2 are just represent which region it is in, right? And similarly, if your Q is more than half full, you say it is the second value. So 1 bit of queuing information. So meaning in your system, whatever is your buffer, you send 1 bit about that buffer knowledge to the receiver. Right? So this is basically sort of saying this is the nearly full, this is the nearly empty scenario. Right? So what the receiver does, it uses this 1 bit. So there are two cases now. It uses this 1 bit to quantize the channel. So this is the channel gain. It goes from 0 to infinity. Right? And I'm going to, let's say you have 2 bits of feedback. Right? So if the receiver is, or rather if the transmit buffer is nearly empty, it uses, let's say, these 3 thresholds to have 4 regions, 1, 2, 3, 4, corresponding to 2 bits of feedback. Okay? On the other hand, if your receiver is, or if your transmit buffer is quite full, it uses a different set of thresholds. Right? And the way it works is, if the way I've drawn it, it may not be very obvious, but these thresholds are closer to 0 than these thresholds. It's intuitively meaning you're willing to take more and more of a chance on the channel. You're basically, it will become clear from the next slide too. You're ready to take more and more chance on the channel. So is it clear what the receiver is doing? Right? It uses this knowledge of whether it's 1 or 2, this region or that region, to quantize your channel differently.
So are
They are unequal regions, and the regions are determined by they are optimized to minimize your total error rate. So you can compare it with, for instance, a mean squared error quantizer or something, and it'll be like significantly better.
So how tractable is that optimization problem?
We'll get to that in just a second, but it's a little difficult to do that optimization. It is numerical.
So the answer you gave, I didn't quite understand. You're going to optimize the threshold.
We're going to optimize these thresholds.
The criteria for the optimization
Is to minimize the total error rate.
the big pie.
This big pie.
Is the error rate of the whole thing.
The error rate of the whole system, both the buffer overflow and the what does it? All right. So this is what you do with the transmitter. This is what you do with the receiver to determine the feed forward and the feedback. And then once you get that back, right, what you do with the transmitter to do the rate and power control is as follows. Now the transmitter has knowledge of QT 1, 2, 3, 4, 5. It has this exact knowledge. It also knows what QT hat was because it sent it. By the way, I'm assuming error-free feedback and feed forward. We'll worry about errors later. All right. So depending on what information, remember it gets 2 bits of feedback. Correct? In this case, in the QT hat equal to 1 case, the thresholds are this beta 1, beta 2, beta 3 of 1. Right? So the transmitter, for instance, might make a decision and say, okay, in this region, I will send 0 bits if the queue has 1 packet and my channel gain lies between these 2. Right? Or for instance, let's say the channel gain lies between these 2. Right? That's what my receiver is telling me with the feedback. But I might decide to send 1 packet if the queue has 2, or 2 packets if the queue has 3, even though QT hat was the same for both, because I have knowledge of QT. This is just an example of a rate control policy that it might do. The optimization determines all these numbers. What is 0, 1, 2, all these numbers are determined as per.
What is Y?
Y is the number of packets transmitted. Y21, for instance, this 1 is the common, 0, 1, 2, 3 indicates which region it is in, right? And the first substrate tells you what the queue size is. So Y32 is the number of packets sent when the queue has 3 packets, and the buffer or the feedback tells me it's in the second region, 0, 1, 2, 3 region. Right? So I want you to realize that these numbers could be different because precisely of the fact that I'm not just using QT hat, I'm using QT and this knowledge to determine what. Similarly, if my QT was 4 and 5, the thresholds are different. Right? And it uses this knowledge, these thresholds, to again say, okay, in this case, for instance, even though the channel could be really bad, my buffer is full. 5 is the size of the buffer in this case. Right? So there's no point for me just waiting because anyway it's going to overflow. I'll just take a shot and send 1 packet on the channel. Right? I'll take my chance with the channel. That's basically what it's saying. Right? Question so far? So as I said, these numbers 0, 1, 2, 3 and so on are the rate control policy that are determined as part of this optimization. Questions? So I have a couple of more pictures. Well, this I've already mentioned to give you an idea. So this function f, this rate control policy, the number of packets transmitted, essentially has a flavor like this. So when the buffer is 1, right, there is a threshold. If it's less than the threshold, you don't send. If it's greater than the threshold, you send. The standard thing, right? This is probably what we might do. If you have only one buffer, if you have only buffer of size 1, packet comes in. If it's greater than the threshold, you send. Otherwise, you don't. Right? If your buffer is of size 2, what you do is you might decide to send when it is here. So this packet gets queued up, it goes here because QT becomes 2. And if the channel gain is very high, you send both the packets. If the channel gain is really low, then you don't send anything. All intermediate ranges, you send 1. Or in other words, I want you to realize that the threshold for sending 1 packet decreases as your buffer size increases.
Why did you take a chance and transmit it anyway when the buffer was full, like 5 packets? Why did you take a chance?
Why did we take a chance? We might end up taking a chance. I'm not saying this is the solution. If the optimization tells you Wi-Fi 0 is 1, that means you're taking a chance. It is telling you statistically it is better for you to take a chance rather than wait and know for sure that you're going to suffer a packet. Why might you not always want to do this is because you're wasting power by taking a chance. right? So depending on how much power constraint you have and so on, it might be worth taking a shot, taking your odds on with that, or it might say, oh, don't waste your power, conserve it, put this 0.
Was there a delay constraint? It was not there in the optimization problem.
The delay constraint is hidden. Basically, the buffer length serves as the delay constraint. So if you have a first in, first out policy, right, and you have a finite length buffer, the length of the buffer serves as a bound on the absolute delay. So the delay constraint gets hidden in there. Questions? All right. So they said, I want you to realize that the threshold for sending one packet keeps decreasing as your buffer keeps increasing. And the same thing for sending 2 packets. So the threshold for sending 2 packets when you have buffer of 2 is very high, whereas when your buffer is full, the threshold is much lower. Right? So this is what we intuitively expect. We don't impose this as a constraint, but this is how the solution that comes up ends up having this sort of behavior. So the thresholds are like this is between these two, and then this will lie between this one and that one, and so on. Right? So that's a property that is very intuitive, and it shows up as a result of the optimization. We don't have to impose it artificially.
But if you don't have the number of feedback, right? Your feedback base is fixed.
Absolutely, absolutely. So that's in fact what the next slide will sort of talk about. So in this case, for instance, what will happen is if this is a threshold, this 2, 3, 4, 5, let's say there are 5 thresholds. That means if you want these 5 to be individual thresholds, the number of feedback bits that it corresponds to is log of 6. Right? So given number of finite feedback bits, for instance, you might have buffer of size 10, but only 2 bits of feedback. Right? In which case you may not be able to afford yourself this many distinct thresholds. What will end up happening is that maybe I don't have that slide. These thresholds might start coinciding because you only have a finite number of bits of feedback. You may not be able to afford yourself all these many feedback bits. This is just to conceptually explain the process of what I just did.
So the aim here, are you trying to do like one-shot optimization for the channel?
One-shot statistical optimization based on knowledge of the arrival statistics and the Rayleigh fading, if it's a Rayleigh fading channel. And right now I'm assuming IID between time slots. So you don't need the IID assumption, but basically based on those assumptions you do the optimization, and the thresholds are assumed to be known at both the transmitter and receiver. And that's not unreasonable because once the statistics are known, you can assume both the transmitter and receiver know the statistics and they can do the exact same optimization. So they will know the thresholds.
Essentially,
Both.
the channel statistics should not change. Right?
The channel statistics don't change with time. If it starts changing with time, you redo the optimization. So, okay. All right. So we're running out of time. So this one is basically what I call as a comparison with statistical transmit buffer information, meaning the receiver does not know the transmit buffer. There is no feed forward, but nevertheless, it knows that there is a buffer, and it knows what the arrival process is, and it knows the statistics of all those. Right? What happens there is that the thresholds are the same. It does not change with your queue information. The thresholds are fixed: beta 1, beta 2, beta 3. Right? Because I don't have feed forward information, right? The thresholds are fixed. This is sort of like our normal case, with the only difference is that the thresholds are again generated to minimize your outage, in which you are implicitly using knowledge of the the arrival packet sequence. So if I'm not confused people enough, let me try this again. You don't send any feed forward information, okay? But nevertheless, the quantizer thresholds that are being generated are not a mean squared error quantizer. Right? The quantizer thresholds that are generated depend on this the rate control policy that you do, and the arrival statistics of the packet and the buffer size. Right? It does not depend on the number of packets in the buffer or anything like that. It just says, oh, I know he has a buffer of size 100 and he is going to be sending this packet, and these are the delay constraints and so on. So let me optimize these thresholds to minimize the total error rate. Rather than use a mean squared error quantizer,
But
we are using a different.
Are fixed at this point.
Which one?
The thresholds.
The thresholds are fixed.
So it's sort of your best without a feed.
This is your best without your feed forward. Exactly. These are fixed to the best values without any feed forward, because it's the same for all Q. This is sort of a comparison point to show the comparison of why the real-time feed forward will help.
But since you know the statistic arrival properties, right, and you know your parse channel states, can you sort of estimate how many packets are in your buffer now from the receiver?
Absolutely. Absolutely. You could do that, and in fact I briefly talk about that. You could do that, but what we are doing here is actually you're using not the statistics of the arrivals, you're using the real arrivals in the feed forward case. Right? It's the same thing like in your channel state information, right? You have statistical channel state information at the transmitter. Right? So you can do your same old your estimates and so on. An exact analogy of that is if you knew the statistics of the arrival process, you can try and estimate how many are in the buffer and so on. You could do that. We haven't done that, but yeah, that's the exact analogous of statistical CSIT and instantaneous CSIT, statistical transmit buffer information and instantaneous transmit buffer information. Right, the exact analog of those. Right. So let me go on and talk. The optimization is very difficult, I think, because of the fact that you have a buffer and it's a closed loop system. Closed form results have tried really hard as very, very difficult. So we end up doing a numerical optimization. Right? And there are special cases in which the feed forward does not help. One of this was what was pointed out before, which is full CSIT. If your transmitter has full channel information, right, then you don't need feed forward and all this. Whatever the receiver is doing, the transmitter can do. Right? It turns out at the other extreme, when there is absolutely no channel state information also, then at least this type of feed forward does not help us. It might help you with something at the MAC layer or something we don't know, but if there is no channel state information or full channel state information, feed forward does not help. And at the other extreme where the delay is 1, what delay of 1 effectively means is if a packet comes, it has to be immediately sent. You cannot do anything about it. If that is the case, then there is no rate, nothing, right? Whatever comes, you just send it. In that case, your feed forward does not help. So these are all sort of the extreme cases where the feed forward does not help. But when you have finite number of bits of feedback and you allow a delay of greater than 1, which corresponds to buffer of greater than 1, let's say, right? In those cases, channel state the feed forward does indeed help. And to just illustrate the performance, so here these two are. This is the probability of outage. Actually, it should be total error rate because it's both overflow and outage. Error rate as a function of SNR. This is for 2 bits of feed. These both are for 2 bits of feedback. This is 0 feed forward. This is 1 bit of feed forward. Right. So you get about maybe a dB, 2 dB, depending on where you are. Here you don't get much, but maybe there you get about 2 dB gains in performance. And this is the same thing with 4 bits of feedback. This is 0 bits of feed forward, 1 bit of feed forward. So you get like about a dB gain in performance. And same thing for a buffer size 3. Now you can actually go to feed forward of more than 1 bit. You can say, what if I have 0, 1, 2 bits of feedback? Feed forward. And as you might expect, each additional bit only gives you incremental gains in performance.
So the statistics of the buffer getting emptied basically is a complicated function of what feedback you're getting and the loop that you have, right? The buffer state actually behaves like is modeled as a Markov process. Right. But the server is it's a complicated. It's not like a simple exponential service type server.
It's not an exponential service server or anything. The output of the server is your rate control. How many packets you remove from the server at each time depends on that rate. This rate control RFT this function, this f. That's what is your output. So it's not a neat any known form like MG system or any of those systems.
So that you're computing numerically.
The whole thing is modeled analytically as a Markov process. The solution is the final thresholds are solved numerically. So we have complete closed form for saying this is the total error rate in terms of the thresholds. All that can be done analytically. So the taking care of that buffer thing can be done analytically. It's only the solving for the thresholds that cannot be done analytically.
So how do we get the probability of
buffer overflow?
Yeah.
The probability of a buffer overflow, for instance, let me go back to let's say this case, right? So the probability of buffer overflow, if you know the arrival of a packet, let's consider on-off traffic. Okay, simple on-off traffic. So you either get one packet or you don't get a packet in each time slot, right? So in such a case, the probability of buffer overflow is very easy. All it is, it's the probability of being in of Qt equal to L multiplied by the probability of the channel being in the state condition on Qt being L. And since they're independent, it's basically that. So only if the channel gain lies between these two and Qt is L is buffer overflow, right? Because you're not sending any packets, your buffer is at its limit of L. You get one more packet. You have to multiply that by the probability of a packet arrival, since it's an on-off traffic, right? And if you knew the on-off traffic probability of arrival, that multiply the probability of channel being here, multiplied by the probability of Q being there, will give you the probability of buffer overflow. If it is more sophisticated than an on-off traffic, you might have buffer overflow even here, right? For instance, if your buffer is 5, and it is likely that there is a finite probability that you might get 6 packets, right? Then the probability of being here times the probability of being Qt equal to 1 times the probability of getting 6 packets, right? So it can be calculated simply based on the
So you're able to get like an analytic expression for the Q being first probability.
Correct. You can get an analytical expression. You can get analytical expressions for the probability for the PMF of Q occupancy. So you can know what is the probability that the queue is full, the queue is empty, queue is 2 packets, and so on. We can do that completely analytical. Right? So bottom line, it gives gains about a dB sometimes, maybe a little more, maybe a little less, but needs a lot more exploration to figure out, when you get more gains. And I have some ideas as to when I think more gains will be obtained and so on. It depends on the variance of your input. If your input is very high variance, then the value of the feed forward will increase. It's same like your channel. If your channel gains are like meandering along, then feedback doesn't really help you, right? You might as well be able to know that beforehand or estimate that beforehand, right? So only if your channel goes through deep fades and so on, then your channel state information gives you more value. Similarly, if your buffer, or rather if your arrivals goes through large, it's very bursty, like an MPEG or something like that, then it will give you more. The value of a feed forward would probably be more. Again, this is a gut feeling more than anything else. Right? Now, in terms of protocol information, I think we may have spoken about this question earlier. In any multi-rate system, the transmission rate has to be sent to the receiver. And in practical systems, we might do it explicitly. In cases, we can do it using a blind scheme, meaning, for instance, if you use different constellations to send at different rates, you can figure out what the constellation is, and from that you can figure out what the rate is. So you might be able to do a blind transmission, but let's not worry too much about that. Let's just say, typically we send explicitly, okay, now I'm going to send at 10 kbps, now I'm going to send at 20 kbps. Right? You're sending an explicit transmit information. Instead, an alternative is to send this transmit buffer information. Right? Once you send this transmit buffer information, then the receiver can make the same rate control decision as the transmitter did in determining the transmission rates. So the point I'm trying to make here is, it's not like a totally new type of feed forward information that we have to introduce. It could replace this explicit rate transmission that is normally done. If you have a multi-rate system and you explicitly mention the rate, instead of doing that, if you use the transmit buffer information, if you send that, it's no additional overhead in the feed forward. You can just do the exact same thing. Right? All right.
Well, they're not exactly the same. They seem to a ballpark comparable.
Yeah, that was, again, I didn't put any numbers or anything there. It's because the amount of, you may have only 4 or 5 different rates, so you need log of that many number of bits to send that rate, whereas your feed forward might be more. You might want to send more or less or something, but more at a qualitative level rather than at a quantitative level. People have been sending some feed forward, is what I was trying to motivate and say. Right? So now that was all. As I said, we used Shannon's capacity formula for each fading state. But we can do the same thing with, let's say, for instance, we are going to use a multi-modulation scheme. So we're going to fix the packet size. We're going to fix the channel code to a rate half code, some standard constraint length. Rayleigh fading channel, perfect CSIT at the receiver. One time slot is 50 channel symbols. And in this case, I considered just constant rate packet arrivals, but well, actually, we will consider other rates too. 3 different transmission rates. The point I'm trying to make is, let's say you use these 3 different modulation schemes to send 2 bits, 4 bits, or 6 bits, which let's say correspond to 1 packet, 2 packets, or 3 packets over 50 symbol period. All right. If you were to use this type of a constellation scheme, right, and you plot the packet error rate versus SNR for each of those. So this is your standard QPSK, this is 16, and this is 64 QAM, right? So this is your standard packet error rate versus SNR for each of these schemes, right? So what we might have to do in a real system is, let's say you pick the packet error rate to, I think this is 5% packet error, 10 power minus 2, so 5% packet error rates, right? For that 5% packet error rate, you can plot what is the SNR, or equally the transmission power required to send 1, 2, or 3 bits, or 3 packets per second. Right. What I'm trying to motivate here is, instead of using that P equal to exponential, you can use this where you take your packet error rate into consideration. Right? And once you have the packet error rate into consideration, you put that back into your optimization, because now the rate and so on is a function of this channel FER, frame error rate or packet error rate. Right? So basically we can do this, you can put that into the picture and take into account the fact that even when I said perfect transmission, no outage occurs, right? Outage might really occur with a frame error rate. So you put that also into your total packet loss rate. Right? So simply want to motivate that it can be done with a real system, and this is just showing the effect of each feed forward bit. Right? So in this case, I've plotted 3 different. This is the total error rate, packet error rate, versus SNR or power. Right? This curve is for feedback of 2 bits, 0 bits of feed forward. This curve is 3 bits of feedback, 0 bits of feed forward. This curve is for 2 bits of feedback and 1 bit of feed forward. Right? So the question essentially is, I mean, the sort of what I wanted to show here was, 2 plus 1 is 3. Right? So you're sending 2 bits feedback and 1 bit feed forward. Is that equal to or less than or better than sending 3 bits feedback? Right? So which is better? Does it make sense to add this new channel feed forward, or should you just send a feedback? And in this case, it turns out that if the 3 bits of feedback is better than 2 bits of feedback and 1 bit of feed forward. Right? But nevertheless, 1 bit of feed forward does improve your performance beyond just 2 bits of feedback. Right? And remember, this feed forward is also going to be used in the MAC layer by other schemes. For instance, right, if let's say we are talking of an uplink, distributed uplink, I am trying to schedule users, different users. I want to give weighted priority to the ones whose buffer is nearly full. Right? I'm not just going to use the channel information. So that's why this feed forward can actually have utility in other places at the higher layers and so on. So it's not purely saying, oh, okay, it's better to just increase my feedback, then I shouldn't worry about the feed forward. I think we have to carefully consider and say when it makes sense to use both, or how to use both in advantage. If you can actually use 3 bits of feedback, maybe do 3 bits of feedback plus 1 bit of feed forward, so which will take it even further down. Right? And just the same thing for another case. And so basically to summarize, I think we show that similar outage performance can be achieved using different feed forward and feedback bits. So is 1 bit feedback better than 1 bit feed forward? We don't know. And as I said, my gut feeling is it depends on, if you were to do very bursty traffic, then the answer might flip around. And one of the difficulties we have is
the
that
example you showed, though, the feedback bit was more valuable.
In that it was more valuable. I'm not sure.
No proof of that.
We have no proof of that, and my gut.
Example where it works, where it doesn't.
Which is exactly what I was. Unfortunately, no, because the optimization is very difficult to do. So I was trying to do for very large bursty sources. You need more buffer size, and the size of the optimization blows up very quickly, because if you have like 2 to the number of feed forward into 2 to the number of feedback times the buffer size, that many number of variables, solving them numerically is just proving to be a nightmare right now. That's basically the point. So that was my gut feeling statement. Based on what we have, it seems like feedback is better, but I don't think that is necessarily true. And if you change the distribution from a Rayleigh fading to something, I think Kyrie once did, like these uniform distributions and so on, then things can change differently. Right? So, and we want to understand this trade-off between buffer overflow and packet loss in the channel, because this whole optimization that we are doing is taking both into account, right, and saying, oh, sometimes it is better to do that, sometimes it's better to do that. We need a more analytical understanding and grasp of how exactly that is. We need to find out analytical expressions for the error rate versus SNR, which will be useful in solving them, solving the optimization problem. And of course, we have to study the effect of errors in the feedback and feed forward. We have completed the effect of errors in the feedback. It just adds another term to your total error rate in terms of based on the error rate and the feedback information. And we have to study the dynamics of channel and source variations, take care of channel estimation errors. So it's almost like a laundry list of things to do, but some of them are in progress, some of them are.
So all the experiments you did were with IID channel processes?
IID channel processes, correct.
So you could do some really complicated, if you could figure out how to do the optimization, like if you had a correlated channel.
Correct. With correlated channels, actually you can do one more thing, which is that your, maybe I'll go all the way back to. So this, with a correlated type channel, remember this buffer feed forward that you're sending? You can actually make this a function of the current buffer state and the past estimate of your channel. So I can put gamma t minus 1 hat here. So I can actually change and say the forward information that I sent to you depends on the estimate of the channel in the previous time slot if the channel is correlated. So we can actually add another layer of complexity into the design.
Is it obvious how to even set the transfer power? Like you get this quantized channel feedback,
right?
And you showed us that it all maps to, ultimately it maps to there's this curve that's given a certain channel state, right? The quantizer will report something, and then based on the buffer, every channel state you have this increasing number of packets.
Correct.
Sent.
Correct. That is this curve, basically. I think is what you're referring to.
Yeah.
Right. So, can you repeat your question again? Sorry.
Yeah. So I suddenly lost track of my question. Do you remember what I was going to ask? Oh, the power. Yeah.
Yeah, the power.
So is it clear what power level to use when you get the quantized channel state feedback?
Yeah. So there are two things. So in the first case, the power level I use, for instance, if I know that the channel lies in this region, and if I know the buffer is size 2, and the channel is here, that means I have to transmit 2 packets. That means the power I use is going to be of the form e to the 2 minus 1 divided by this gamma.
So you're sort of allowing yourself to use
infinite.
You're assuming sort of the worst gamma for the.
Exactly. Correct.
That seems like that's just an arbitrary.
It is an arbitrary choice, and that's actually I got the same question at an earlier conference also, and I went and tried something, which is suppose you were to not send e to the 2 minus 1 by this gamma, but some gamma that is here. Right, so that you can guarantee that in this region there is no outage, but in this region there is outage, which is sort of the question I think you're basically asking, right? In some cases, it turns out the performance, though not the same, is not very different.
In simpler settings, I've written some papers about this. I don't remember what the answers were.
Okay, but that's the exact same question I got. Is why don't you just why do you want to take the worst case channel and divide by gamma of this to ensure no outage completely here? Why don't you take a chance and say you set some other value here so that there is still a finite probability of outage there and only no outage there, right? Another thing I would say is in the second part, we don't do this 1 by gamma. I don't do this. What we instead do is you've set a frame error rate beforehand. Right? So depending on that frame error rate, let's say 5% and so on, we use the transmission power that sort of guarantees 5% error rate in that transmission, whether you're sending 1 packet using QPSK or 2 using 16 or 3 packets using the 6-to-4 count. So it's an open question. I don't know the answer, and it's certainly something that should be considered. So bottom line, I think I wanted to use the fact that there is this whole new schemes of transmission schemes where you could use feed forward information, and there's the at least hopefully have motivated people to start looking at the reason to send feed forward information to the receiver, so you can use that in improving your system performance. Right? How are we doing on time?
Oh, we're fine.
2:30? Okay. Should I go into the next half of the talk, which is totally not on this, or should I stop, or what do you want to do?
Well, 10 minutes.
I'll give you a brief outline. I think that is that's easier to explain. Again, so this is what we call the Gaussian soft channel. Sorry?
I didn't realize it was a half, but
Sorry. This is not equal halves. Let me put it that way. Yeah. So basically, I think this is fairly easy to motivate. With mobility, there's a lot of handover across base stations that everybody is familiar with, and So what we are going to consider when a Gaussian soft handover channel is basically, let's say, a two transmit and two receiver system, right? Your standard time invariant Gaussian channel. So we're not talking of fading, we're not talking of anything, right? So your receive signal is given by the standard linear combination of the transmit and the noise. And further, I've sort of normalized this. There's a traditional normalization where the two main channels have gains 1 and the other two are gains C. Right? So we're going to consider the standard 2x2 channel. Okay? So that's for simplicity, we are considering Gaussian code books too, meaning the transmissions use Gaussian code books. Right? I think I may have. Okay. No wonder one of my slides was missing, but I think it's. Let me go on. It may have gone out of sync. So this is a standard interference channel, right? Right. So this guy transmits here, this guy transmits here, and there is interference in those. Right. By the soft handover channel, what we basically mean is that this transmitter can be decoded either here or here. Meaning, parts of this message could be decoded here, parts of it could be decoded here. We allow joint decoding. We don't allow joint decoding, meaning we cannot say, oh, you put the signals of these two together at one place and then decode them. If you do that, you basically get a 1x2 MIMO system. Right? So we're not considering MIMO transmission. We are saying we don't care where he is decoded. He can be decoded here or here. And sort of the motivation to say that was, ultimately they anyway go through the same backbone and reach some destination. Right? By allowing the fact that you can decode them and send parts of it together, we are talking of some sort of cooperation at a networking layer, rather than worrying about fine synchronization at the physical layer and saying, oh, the signal from here and the signal from here has to be finely synchronized. Only then you can put them together and you get your MIMO part. Right? So the basic question we are asking is, if you can allow this guy to be decoded here or here, and similar this guy to be decoded here or here, or some parts here, some parts there, what should you do? What is the capacity region and what happens? And that's basically what we call the soft handover channel. Okay, and in terms of the interference channel, as you might have expected, the interference channel, the capacity is known in special cases, what we call strong interference, very strong interference. In the other cases, there's only an achievable region known, and there's like the traditional Han and Kobayashi's famous technique of private and public messages and take convex combinations of all those. And there's also more recent work by Igal Sassoon that gives you a nice sort of time sharing way of looking at the achievable region for arbitrary interference channels, right? So as I said, in special cases capacity is known, in other cases only an achievable region and an outer bound by Kramer is known, right? So what we end up doing is basically we want to, as I said, compute the achievable region of this soft handover channel, where Ri is the rate at which independent information is sent from node I to the base station. So some information can go here and some information can go there. The sum of those two is Ri, the rate for user 1. So what pairs R1 and R2 are achievable? That's basically the question that we are after. We don't have the capacity region, but let me get to the interesting point. A simple outer bound, of course, you can do a 1x2 MIMO, or you can, for R1 is a 1x2 CMO, right? And for R1 plus R2 is a 2x2 system. These are outer bounds, right? So you can never do better than this. So feel free to stop me. I'm rushing through the slides here.
So why isn't the R1 plus R2 bound like a MIMO, but it should be a map, right? Requiring, like you'd get a better outer bound by assuming independent
but it's so the MAC aspect doesn't come because now you have okay, it's actually a MIMO MAC. Okay, it's a MIMO MAC. I should have been more right. So it's a MIMO MAC. Correct. So that's a simple outer bond. Yeah, I should have mentioned it as a MIMO MAC. That's correct. Right. So in terms of the achievable region, this does not seem like a big deal. I mean, as in it says, you can do this interference channel where you decode this guy here, or you can decode both of them here, you can decode both of them there, or you can decode this user there and that user there. Sort of take all possible combinations, right? So these two become like a MAC, these two become like an interference channel, right? That seems to be what this soft handover channel achievable region would be, and it is. You take the convex combination of all these things, and you get an achievable region. Right, so let's see how that looks like, and so this is a standard, simple, symmetric case. Yeah, so this is one of the MAC capacity regions on R1 and R2. This is the capacity of the other MAC, the two reds, and this blue is the capacity of the interference channel, because you can see it's of this form. These two are very strong, and the interference is very weak. So one of the interference channels actually gives you that. The other interference channel will actually give you a capacity which I have not shown, which is actually the intersection of these two MACs. Alright, so bottom line, the interference channel capacity equals this soft handover channel capacity region in this case. Right, so you decode user 1 at base station 1 and user 2 at base station 2. Right, essentially you're decoding at the base station with the highest SNR. So the question is, so what? So what's this?
Say it again. So you get this achievable region by considering the union, the sort of the
of these four decoding.
These four things.
Correct.
And you found that achievable.
Out of these four, these two MACs are what the two red curves that I showed. These two red.
Yeah.
And this interference channel is the blue, outer blue.
Okay.
And this interference channel I have not shown is actually this small region right here.
Okay.
It's that smaller region.
And then you said something like.
So if you take the combination of all four,
Yeah.
we basically end up getting this blue again.
Okay.
Right? Because the blue sort of dominates everything. Yeah. All the others are contained inside the blue. Right? So the blue is the dominant one. That's why we said the SHC soft handover channel achievable region is the interference channel achievable region. Right?
Okay, the terminology of the IC achievable region.
IC is interference channel achievable region.
Yeah, it's a funny terminology.
Yeah.
What you're doing is it's the IC with single user decoding.
IC what?
I mean, you're not, when you do this, right?
When I do this?
When you do this, right, you're just living with the interference from the other transmitter.
No, I did not say that. I'm just saying I'm treating this as an interference channel. What might end up happening is I might be able to decode this guy here and cancel it out and then transmit that. That's in fact precisely what happens here. You're not doing single user decoding. You're actually doing joint decoding. It turns out that you will be able to, whatever rate this guy is sending to him, you will also be able to decode here, remove that, and then decode him. And vice versa for this guy. And that's basically what a strong interference channel is. So because the channel gains are like 0.3 and 1, right? So all I want to say is we are not doing single user decoding. In some cases it might turn out to be single user decoding, but what we are actually doing is the best possible decoding scheme. If someone comes and tells you you have to decode.
So in the picture on the left, like there's a specific coding strategy you're using to get that blue curve.
Correct, right? Yes.
Are you doing Han Kobayashi or
We're not doing the Han Kobayashi, we're doing the Eagles-Hassan coding scheme. The other one, which is the time sharing between two different code books. Basically, they're Gaussian type code books.
Okay, all right.
That's the easier one.
You're calling the IC
achievable region. Correct. That's the Sasson achievable region. So out of these, we are doing actually this, which is the one given by Sasson. We are actually doing this is the achievable region for that interference channel, for both the interference channels. This is actually a lot more harder to do and write analytically. It's Han Kobayashi because it's correct. So as I said, So what? Right now all we have said is, yeah, you take the combination of all possible decoding schemes, and in this case it turns out you have to decode user 1 at base station 1 and user 2 at base station 2. Right? The so what is, I think what happens is that in some cases none of these 4 decoding schemes, none of these 4 component channels dominates the entire soft handover channel. Meaning, so let's take another asymmetric case, right, where this could, for instance, be one mobile being nearly equidistant from 2 base stations. The other base station is about the same distance the other direction away from 1. So it's closer to 1 but further away from the second. Right? So it's not a very unusual system. So in this case, if you plot the achievable regions, the 2 red are again the 2 max. Okay? And the IC, the interference channel, which is you decode user 1 at base station 1, user 2 at base station 2, that gives you this black. That is the achievable region of the interference channel. Right? So if you take the combination of all that, you get this blue thing which is strictly greater than the red and the black. Right? So that really is the interesting thing. So what does it mean? So basically what it means, as I said, the SHC achievable region is larger than any of the MAC and IC achievable regions. Right? So what that means is, if you pick a single base station to decode each user, it does not achieve the boundary of the achievable region. You might have to send non-zero rate of information to both base stations. You might have to send.
So in practice, this will be operating at one point of the curve.
Exactly.
You don't need the entire convex.
You don't need, so it depends. So precisely how, that's precisely correct. And in fact, how we find that is by setting an optimization problem to say you operate either at this extreme where you don't care about that rate, or you operate at some you want to optimize, let's say, some linear combination of these 2 rates.
So let's say you're at a point which is outside each of the max and outside the interference channel.
Say this point there.
So what does it physically mean? Some time sharing between 2 different modes?
Basically, yes. So you want to time share between a coding scheme that decodes it here and a time scheme that decodes it there. Or you can do the same time sharing in sort of in a code sharing type sense, right? So bottom line, you cannot pick a single base station to decode each user, and that will not give you the entire achievable rate. For instance, if, as you said, the operating point is the peak sum rate, right, and the peak sum rate might correspond to just this black interference channel. What that means is, yeah, then you can pick a unique base station and you're okay. Right? But if for some reason the operator wants to say user 1 paid me more money, user 2 made me less, do some pricing based differentiation. So he says I want to give the user twice as much weightage in the rate. So you might want to operate at some point here.
Peak sum rate is E point E rate.
Sorry?
Peak sum rate is at point E rate. R1 plus R2 maximum.
E is just the no, I haven't seen this. E is just the point of the MAC that one of the corner points of the pentagon. I just labeled it E, that's all. It doesn't mean anything.
No, I think that should be the peak sum rate.
Peak sum rate would be that's equal rate. That's equal rate. Peak sum rate could be that one, yeah. It could be the E.
Depends on how the slope of that.
Yeah, it depends on the value. I don't know the exact. So that could be 1.2, 1.5. Yeah, that looks like it would be close to the peak sum rate.
Is that where that curve is from the MAC?
Which one?
So he's saying, well, it's from a MAC, so the connector will be a 45 degree.
Yes, it is. It is a 45 degree line.
But why is
But this is actually greater than that.
greater than that?
So in fact, so the peak sum rate would be the one where R1 plus R2 is tangential to this achievable region. Right? So R1 plus R2 is a 45 degree line this way. So you keep drawing it this way, so it would touch it somewhere there. So it would not be at point E. Right? So, but the R1 plus R2 max might lie on this black curve, which basically means the peak sum rate is maximized by the operating as treating it as an interference channel, picking a single base station to decode each. Okay, so I'm not saying for the peak sum rate you would need to decode at both, but it depends on where in the curve you want to operate. As I said, if you want to operate at this point for whatever reason, meaning you want to give more weightage to R2 than R1, he's paid more, right? Then you cannot pick a single base station to decode. That's basically the point. So all points in the region are not achieved by picking a single user on the boundary. That's basically the punchline, and Well,
So actually, to have this best sort of choosing the best way to decode, you need to have the transmitters are sort of cooperating with each other. Right? They have an agreement. It's not like if you had some sort of game theory framework where one of them, like each of them, just cares about their own brain.
correct.
They won't have.
Then they won't have that. Right now, again, since this is for a time invariant Gaussian channels, everybody knows everything, and it's like the system operator is determining based on this the single same scheme. It's not a game theoretic thing, which is what I guess Narayan, was that you? Okay, I've seen his ID paper. So basically, there's an equivalent effect in the downlink, meaning should you transmit the information to each mobile from only one base station? Again, we are not talking of cooperative distributed MIMO or anything like that. We're just saying, should you transmit to pick one base station to send for each user, and it turns out you may not want to do that. You actually want to send some parts of the information to each user, potentially from both the base stations, independent information. Right? And again, the same thing as before. If you look at the component regions, now instead of a MAC, the two component regions are your two broadcast. So you'll get two broadcast capacities, and the black one is the capacity of the achievable region of the interference channel, whereas the soft handover channel you can actually do a lot better than either of those. So what that means is, if you want to operate, let's say at a point somewhere here, you cannot pick one base station to send information to each of the users. So you cannot say base station 1 sent to user 1, base station 2 sent to user 2. That will not give you that point blue. Yep. So it's mostly of telling us where to do that. Right? So let me just and it turns out there's one single framework to calculate both this uplink and downlink soft handover channel region. What we end up doing is something like the Han Kobayashi, but not exactly the Han Kobayashi. We end up calculating a 4-dimensional region, and we end up taking two different mappings to get the uplink and the downlink case. So it's the same big region. You map it differently to get the uplink and the downlink SHC. And in the symmetric case, we can prove that it is sufficient to pick a unique base station for decoding each user in the uplink. So if the channel is symmetric, then you can pick a unique base station and we are done. Whereas if it is asymmetric, decoding each user does not always. Meaning we still don't have conditions on the asymmetry where you have to pick more than one place to decode, but we have identified cases where it does not happen. And transmitting to each user from one base station is not optimal, even in the symmetric case in the downlink. That's not hard to see, depending on the operating point. Let's say you only care about one user, you don't care about the other user, you want to use all the power towards that guy. Right? So
maybe I missed the slide. You also went into what the downlink looks like?
yes, so the downlink. So this is the downlink software. So in a standard interference channel, there is a unique designated transmitter for each receiver. Meaning, this receiver gets data from here. This receiver has to get data from here.
Okay. So you didn't allow. What you're not allowing is a broadcast channel, a 2-to-1, 2-user broadcast channel.
So like this, without this.
Like the two base stations, but so you're not allowing them to act like a single transmitter with two antennas that is doing
Correct.
broadcast.
Correct. Yeah. So we are not allowing joint encoding. So across the base stations, we are not allowing them to jointly encode and transmit. So we are basically saying, suppose you only allow simple encoding.
So the other distinction seems fairly real.
This is partial. So that was the one that we first did, and then we realized, oh, this is just the same thing that we did there. If you do a different mapping, as we said, we get this. The other motivation could be that, in fact, if these were actually ad hoc networks, think of it. Let's say these are ad hoc networks, right? You remember the David-Say type arbitrary routing type strategies, right? Everybody might have information to send to everybody else, right? So you might actually want to send some part of the information that is corresponding to some destination might be here, some other part might be here. He just sends independent information to them. So making them coordinate in an ad hoc network can be very difficult, right? So at least at the physical layer. So if they were to, let's say, cooperate at the higher layer, maybe. So as I said, you're right. It's the uplink which is really the first thing that we did, and that's the easily motivatable and nice feeling. This is sort of a completion and saying, yeah, same thing, same effect happens in the downlink, but maybe it's not critical. As you said, it may be easy to synchronize them to a clock and transmit synchronized in the downlink. But if that were not the case, what happens is the question, right? And just to wrap up, it turns out that the fraction of data being communicated to each base station could be different in the uplink and downlink. What that means is I might send 70% of my data to base station 1 and 30% to base station 2, whereas in the downlink I might get 90% from here and 10% from there. It depends on what operating point you choose, and even if the channel is symmetric in the uplink and downlink. So if you use like a time division duplex system. So I will stop right there. I think I've taken more than enough time. So again, thanks for your patience. Thanks for inviting me. And if there are other questions, I don't know if you can see my email. Yeah. Yes. Yeah. Or you can.
Thanks.
Thank you. I went way over time, but